All right, so we're in section 2.5, the last section we're covering in chapter 2. Rational functions. So first thing we want to do is talk about what a rational function is. So a rational function we talked about rational numbers a little bit when we were finding zeros of functions. Rational numbers are ratios of integers, 1/2, 3/4, that kind of thing. A rational function has to do with fractions. We're making a fraction out of polynomials. So we have some function, f of x equals, and we'll say n of x for our numerator and d of x for our denominator, where both the top and the bottom, the numerator and denominator, are each polynomials. And that's what we've been working with all chapter is polynomials. So we have 3x to the cube minus 5x squared plus 3x plus 5. That would be a polynomial. We'd have something like that in the numerator, something like that in the denominator. So that's what we're talking about with rational functions. And we're saying that, and we'll say that the domain of a rational function is all real numbers where the denominator isn't 0. So we just don't want to divide by 0. Polynomials are nice, they behave nicely, so we can plug any number into a polynomial. We just don't want to get 0 when we plug in our number and calculate in our denominator. So we don't want our denominator to be 0. So when a question asks you, find the domain of this rational function, for example, so if we have a nice rational function, f of x equals 2x plus 1 over x squared minus 4. We have a polynomial in the numerator, polynomial in the denominator, so we have a nice rational function. When the question is asking us find the domain, what it is saying is, what we're looking for is, where is the denominator 0? And we're going to say all real numbers except that. So we're going to exclude numbers where the denominator is 0. So where is the denominator equals 0? And we're going to exclude those from the domain. And we've practiced with polynomials enough now that we should be pretty good at figuring out where these polynomials are equal to 0. That's one of the reasons we've practiced with that so much. So for this particular problem, where is the denominator of this rational function going to be 0? 2 and negative 2. X equals plus or minus 2. So our domain is all real numbers except plus or minus 2. And depending on your polynomial, it might be more difficult to find your zeros, but that's really the idea here. We're saying where's the denominator 0, and we exclude that number from those numbers from our domain. So any questions on that? Now, some interesting things happen to rational functions when the denominator is 0. So So the graphs do interesting things where the denominators are 0. And our end behavior of rational functions is also interesting, depending on what kind of functions we have in the numerator and denominator. So that's the next thing that we want to talk about, is what happens to the graphs. So we're going to talk about asymptotes. Horizontal and vertical asymptotes. So we have a few rules that go along with our horizontal and vertical asymptotes. But let me grab a picture here so we can talk, so I can show you visually what we're talking about. So let me go here, I'm going to capture this. So there's my picture, and we're going to look at this this thing really quickly. Why did I get 2 there? I'll drag that. All right. So for this function, we have f of x equals 2x minus 5 over x minus 2. Well, at x equals 2, let's stop talking, guys. At x equals 2, our denominator is 0. At x equals 2, we have a vertical asymptote. So if I drew a line in here at x equals 2, like so, my function would get close to this line, but it would never actually touch. So it gets closer and closer and closer to this red line at x equals 2. So we have this vertical asymptote at x equals 2. That's where the denominator equals 0. And we can also see that as we go to the left and to the right, this graph of this function kind of flattens out. And it flattens out close to this line y equals 2. So if I drew a line in here, like so, at y equals 2, my function gets, as x gets really, really, really big, or as x gets really, really, really small, as I go further and further this way, my function gets closer and closer and closer to this line y equals 2. So y equals 2 is what we call a horizontal asymptote. The vertical asymptote is where our function is undefined. So if I plug in 0 into my denominator, I get infinity. So my function gets really, really big or really, really, really small. The horizontal asymptote tells us what happens to our function eventually. What's the right-hand behavior and what's the left-hand behavior? As x gets really, really, really big or really, really, really small, what does our function do? So that's what our horizontal asymptote is telling us. We have some rules when working with rational functions as to how we find our vertical and horizontal asymptotes. So we have this rational function, and we have our polynomial that's the numerator, and the polynomial that's the denominator, and each one is a long, long, long polynomial. Our rules for the asymptotes. We have 3 rules. Our first rule: if the degree of the numerator So that's the highest exponent on our variable, the degree of the numerator, is less than the degree of the denominator. Then we have a horizontal asymptote at y equals 0. Degree of the numerator is less. Y equals 0 is a horizontal asymptote. So that's our first rule for finding horizontal asymptotes. If the degree of the numerator is smaller, and the degree means the highest exponent on our variable, the degree of the numerator is smaller, then y equals 0 is a horizontal asymptote. Our second rule, if the degrees are equal, and I'm going to write n and d here, degree of n of x equals the degree of d of x. So the degree of the numerator and denominator are the same, then y equals, and we find our horizontal asymptote by taking the ratio of the leading coefficients. Is the horizontal asymptote. And by leading coefficient, I mean the numbers in front of the variables with the highest exponents. And we'll do some examples so that this makes sense. So if the degree of the numerator equals the degree of the denominator, we have a horizontal asymptote at the line given by y equals the ratio of the leading coefficients. And our third rule for horizontal asymptotes with our degrees is if the degree of the numerator is bigger, degree of the numerator is greater than the degree of the denominator, then we have no horizontal asymptote. And we'll talk a little bit more about when the degree of the numerator is bigger tomorrow, because there's one special case where we can find a special kind of asymptote there. So if the degree of the numerator is bigger, then we have no horizontal asymptote. So those are our rules for finding horizontal asymptotes. This tells us the horizontal asymptotes, again, tell us our in behavior, our right and left hand behavior of our function. That's this horizontal line. And we'll do a couple of examples here in just a second. Questions on horizontal asymptotes? And again, vertical asymptotes. Vertical asymptotes are where the denominator equals 0. And we get a line at x equals whatever this value is. That's our line is x equals, so we get a vertical line. So we get a vertical asymptote at the x values where the denominator equals 0. And we mentioned the other day that when we were working with our rational expressions and we canceled a factor out of the numerator and denominator, or we canceled something, and we said we had to restrict our domain when we canceled something out. Something special happens with the graphs when we cancel out a factor. We have a hole in the graph. We have a hole in the graph where both the numerator and denominator are 0 at the same time. And that happens when we have a factor that we cancel. So that's going to be our clue that we have a hole in the graph, is we have a factor in the numerator and denominator that we cancel. So this is our clue when we have a hole in our graph, when we cancel a factor. So this is a bunch of rules. They're not complicated rules, but there are quite a few. So let's look at a few examples of how we're going to use these rules. So any questions before we move on? All right, so let's look at some examples, and then we'll talk about how we graph these rational functions. So we have f of x equals x plus 1 over x squared minus 1. And we want to find the asymptotes. We want to find asymptotes of this function. So on this function, the degree of the numerator, what is the degree of the numerator? 1. The highest exponent in the numerator is 1. So the degree of the numerator equals 1. The degree of the denominator equals what? 2. Highest exponent is 2. So our rules say when the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is y equals 0 is a horizontal asymptote. So this gives us our horizontal asymptote because the degree of the numerator is less. Vertical asymptote. Where could we have a vertical asymptote? Vertical asymptote is where the denominator equals 0. Well, we could have a vertical asymptote at x equals plus or minus 1. Well, let's take a look at this function. Let's be a little more careful here. And let's say that f of x equals x plus 1. How can we factor x squared minus 1? X plus 1 x minus 1. So we've been practicing with this for a couple of days. So we could have a vertical asymptote. We have possibilities of vertical asymptotes at x equals plus or minus 1. But what happens here when x equals minus 1? The numerator and denominator are 0 at the same time. So because we could cancel out this factor of x plus 1, we have a hole when x equals minus 1, because I have this factor of x plus 1 in the numerator and denominator. So I could cancel those out, and those both would be 0 when x equals minus 1. So our vertical asymptote is x equals 1 is the vertical asymptote. And this graph looks kind of like the one we just did. I'll make a quick sketch. If we did just a really not very much detail here, my graph would look like this. I would have a vertical asymptote at x equals 1, and my graph would look like this, and it would look like this, and we would put a hole in our graph at x equals minus 1. We'd mark it like that. We make that better on the graph. So that's a very, very rough sketch. We'll talk about doing more detail in our sketch in just a minute. So we use our rules to find our horizontal asymptotes. For this particular one, the degree of the numerator was less. So y equals 0 is a horizontal asymptote. The vertical asymptote is where the denominator equals 0. We have to make sure that the numerator and denominator aren't 0 at the same time, because that gives us a hole in the graph. All right, let's look at another one. For this one, we have g of x equals 2x plus 5 over 4x minus 6. All right, so how do the degrees of the numerator and denominator compare here? They're equal. The highest exponent is 1 on both. So the degree of numerator equals the degree of denominator. I'm just going to abbreviate that as DEG. And I'm going to say degree of numerator equals degree of denominator. So the horizontal asymptote is the ratio of the leading coefficients. The leading coefficients are the numbers in front of the highest powers of x. So my leading coefficients are 2 and 4. Those are my leading coefficients. So y equals the ratio 2 over 4, or I can say y equals 1/2 is the horizontal asymptote. So the leading coefficients are the numbers in front of the variable with the highest power. So y equals 1/2 is our horizontal asymptote. And our vertical asymptote how do we find our vertical asymptote? When the denominator is 0. So we're going to say where 4x minus 6 equals 0, and solve that for x. 4x equals 6, x equals 6/4, or to reduce that, x equals 3/2. So my vertical asymptote is the line x equals 3/2. So if I made a quick sketch of this graph, and we're going to go into a little more detail in just a second, my graph would look something like this. We have a horizontal asymptote at y equals 1/2. So I'd have a horizontal asymptote just above the x-axis, like so. I'd have a vertical asymptote at 3/2, so a vertical asymptote about here. And my graph turns out to look like this. So a very, very rough sketch of this graph. Questions on finding horizontal and vertical asymptotes? And we're going to spend a couple days practicing with this. So, vertical asymptote where the denominator equals 0. Horizontal asymptote we have to pick depending on the degree of the numerator and the degree of the denominator. All right. Now we want, if we're given a graph of a rational, or if we're given a rational function, how do we graph it? How can we figure out what it looks like? So we're going to talk about graphing. So graphing rational functions, we're going to use the same ideas that we talked about when we graphed other kinds of functions. We want to find several things about our rational functions. We're going to find, listen up guys, to graph rational functions, we want to find the x-intercepts. The x-intercepts. That is where our function equals 0. And when we have a fraction, our function equals 0 when the numerator equals 0. So we can find the x-intercepts where the numerator equals 0. So we just have to set the numerator equals 0. What does the x-intercept tell us? Where the graph does what? Crosses where? What is it? Crosses the x-axis. So this is going to tell us where the graph crosses the x-axis. So when we're graphing these functions, we find the x-intercepts. We want to find the y-intercepts. To find the y-intercepts, we plug in x equals 0 and come up with a number. And the y-intercepts tell us what? Where it crosses what? Where it crosses the y-axis. Y-intercepts tell us where it crosses the y-axis. So those are two things that we're going to figure out, about our rational functions. The other things that we're going to figure out are our asymptotes. So we want to find the vertical asymptotes. We find the vertical asymptotes where the denominator is 0. We find our horizontal asymptotes. And for those, we have our 3 rules. And this gives us a line y equals something. I'm just going to put a box there, y equals something, for our horizontal asymptote. And then the last thing that we do is we plot additional points. To figure out what our graph looks like, we plot additional points. That just means we plug in some numbers for x and calculate. and we'll get some y values for these various points. And then we can plug them in, we can plot them to get an idea of what our graph looks like. So between all of these things, we will have a pretty good idea of what our graph looks like. So I just want to do one really quick example of sketching a graph of a rational function, one really easy one. We'll do a couple more examples tomorrow. And then we'll talk about a special kind of asymptote tomorrow. So these are the things that we're going to do every time we want to graph a rational function. So we have f of x equals x plus 1 over x. So our x-intercept is where the numerator equals 0. So our x-intercept is going to be where x plus 1 equals 0. So x equals minus 1. So it's going to cross the x-axis at x equals minus 1. Our y-intercept, we plug in x equals 0. If I plug in x equals 0, what happens when I plug in x equals 0 here? Can I plug in x equals 0? What happens at x equals 0? It's undefined. At x equals 0, I'm dividing by 0. X equals 0 is undefined. So I have no y-intercept. No y-intercept. So my graph isn't going to cross the y-axis. Well, we just decided that the denominator is 0 at x equals 0, so I have a vertical asymptote. At x equals 0. And I have a horizontal asymptote. I use my rules for horizontal asymptotes. How does the degree of the numerator and denominator compare? They're the same. So when they're the same, the horizontal asymptote is the ratio of the leading coefficients. The leading coefficient here is 1. The leading coefficient here is 1. So y equals 1 is a horizontal asymptote. And I can plug in some additional values for x. I'm not going to go through the calculations, but if I plug in -2, I get 0.5. If I plug in -1.5, I get 0.33. I'm just plugging in values of x and calculating. And if I plug in 1, I get 2. So from all of these, I can sketch my graph. So here are my axes. I'm going to sketch in my vertical and horizontal asymptotes. My vertical asymptote is at x equals 0, so the y-axis is a vertical asymptote. Horizontal asymptote is y equals 1. At -2, y equals 0.5, so my graph is here. At -1.5, y equals 1/3. So my graph is even smaller. And at x equals 1, my graph is up here at 2, above my asymptote. So that tells me my graph looks like so, and like so. And if you're not sure exactly what the shape is going to be, plot some more points. Figure out where your graph is going to go. Just plug some values into your function and plot points. This is our intercepts. And here is where it crosses the x-axis at x equals -1. It doesn't cross the y-axis. So this is a graph of our function. We'll do some more of these graphs tomorrow. Questions? All right, homework. All right, and that's it.